Okay. So again, remember we're working on the fundamentals of electrolysis, and really this is more like it's like adding fundamental concepts to the rest of your electrochemistry, okay? So there were many things that we didn't really talk about in the electrochemistry. We've always used approximations, right? And they work okay. I mean, they get you close enough. But for example, the magnitude of this applied voltage that you have to apply to that cell, any cell, has never actually been E cathode minus E anode alone, okay? There was always other concepts that we really should have talked about, but we had enough to learn, right? So now we can just add these little concepts at the end, and that'll give you better approximations, okay? So this right here is the formula of that magnitude of voltage that has to be applied to an electrolysis cell, but in reality, this would also apply to all the other concepts we've talked about, okay? We just typically set them up so we minimize these to a degree. However, so you recognize the E cathode minus E anode, right? You're okay with that? That's the two half cells. In this case, they'll be in the same solution, right? Okay, so you have two more terms. You have minus IR and minus the overpotentials. The overpotential here is the voltage that's required to overcome the activation energy of an electrode reaction. Greater overpotential is required to drive a reaction at a faster rate. Though keep in mind that voltages are like a potential energy. They're a derivative of energy. If you apply a very, very large voltage to something, you can start getting side reactions, right? Kind of like if you were to go into organic lab and heat everything at 500 degrees Celsius, you just burn everything, right? Okay. So you don't want to just crank this up to the highest it'll go. You'll start getting reactions you don't want, okay? And some of these can become very, very serious. For example, you could start hydrolyzing the water, right? And start getting hydrogen gas, which would then blow up. Okay, IR is the ohmic potential. That's going to be the voltage that's needed to overcome the internal resistance of the cell. So everything has a resistance, right? Except for a superconductor, theoretically. Though I actually don't think superconductors have zero resistance. I think they just have something approaching zero, as far as I'm understanding them. But I'm not an expert in superconductors, so. Go on to more advanced courses, okay? You can find an expert in graduate school. All right. I know, we finally found something I'm not an expert, right? Yay. Okay, so remember that you have to overcome resistance, right? And so you'll have to apply a bit more voltage than you normally would. This is not normally a huge amount of voltage. It's usually like less than 5% of your voltage. So it's usually a pretty small number. But it does matter when you're talking about counting numbers of electrons that went into this reaction, right? Okay. So there is ways to minimize this. For example, a Lugin capillary will allow us to measure an electrode potential with minimal ohmic losses. So you can minimize this number. Did these make sense so far? Okay. So really, those always existed. We always were sort of ignoring them, right? Now it matters because we're counting numbers of electrons going over. We're counting on these things, right? Okay. So concentration polarization is going to occur when the concentration of the electroactive species near an electrode is not the same as the concentration in bulk solution. Concentration polarization is embedded in the terms of E cathode and E anode. Notice these are not with the knots or primes. So these are the numbers that you would actually get from an experimental situation. Experimental situations will always have a concentration polarization. where the charged ions will be near the cathodes and anodes because they're attracted or repelled, right? So overpotential, ohmic potential, and concentration polarization always oppose the desired reaction and require a greater voltage to be applied for electrolysis. They're always going to drain the voltage that you would otherwise use for the reaction. Okay? They always work against it. So these factors of voltage greater than 0.893 volts is needed in order for electrolysis to occur, because these take away so much of your voltage. Anything under this is essentially like not doing anything at all. Okay? You'll never overcome the activation energy. You'll never overcome the resistance. You'll never overcome the polarization. By the way, polarization occurs very soon after you start the cell, if you're curious. Like yes, there is a moment when you first start that there won't be polarization, mostly. But it happens within like microseconds. It's very fast. Okay. Oh, the reason I mentioned that, by the way, there is actually experiments you can do that measure this concentration polarization and tell you things about your system, which are like these fast response experiments. They're kind of cool. They take extremely fast responding instruments, so it's very, very fast. Okay, so overpotential for gas evolution at various current densities is right here. And so you can see the different overpotentials here. These are the different electrodes. These are the different gas densities, well, current densities for these gas evolutions. By the way, notice this number, this is amps per meter squared. So it's an area where amperage is being applied. Okay. All right, so suppose we electrolyze I minus to I3 minus in a 0.1 molarity Ki solution containing blah blah number of I3 minus. At pH 10, the pressure of H2 is 1 bar. Let's find the cell voltage if no current is flowing. Then we're going to suppose that the electrolysis increases I3 minus to 3.0 times 10 to the negative 4 molarity. Notice that'd be a factor 10 increase. But other concentrations are unaffected. Suppose that the cell resistance is 2 ohm, the current is 63 milliamps, and the cathode overpotential is 0.382 volts. The anode overpotential is 0.027 volts. What is the voltage needed to drive the reaction? Okay, so let's do A first. Find the cell voltage if no current is flowing. All right. So what is the open circuit voltage on these systems? Well, we typically do E cathode minus the anode, right? So what is your cathode? What is your anode? Basically, what is your oxidation and reduction, right? Okay, so what do we see here? Well, we see an I minus and I3 minus, right? We also see an H2O going to H2 and O minus. OH minus, right? So if we think about this H2O going to OH minus and H2, well, these are neutral again, right? The H's are neutral. The OH has gained a negative charge. You see that? This is an easy way to tell redox versus oxidation, by the way. So you look at these two. If it splits into two equal components, or just a series of components, and one of them has a negative or positive charge, that tells you whether it's been oxidized or reduced. So this right here has gained negative charge, meaning it's reduced, doesn't it? This right here has lost negative charge. See that? We had 3 negatives, now we have 1 negative. And so that would have been the oxidized. That tells us cathode versus anode, right? Okay, so our cathode is the reduction, anode is the oxidation. And the I's over here, by the way. Just a typesetting problem again. Just be used to the typesetting problems by now, hopefully. Because every damn thing I take from your book that they gave me from your book that has it, I don't know. Anyways, we look these up on our normal tables. So we have our E naught for each of these, right? And we see them right there. So we are not in an E naught condition, are we? Notice these concentrations are not unity, right? They're not all 1 bar, 1 molarity, that sort of thing, are they? So we're going to have to go ahead and use our Nernst equation to do this problem, right? So we have to set up our E cathode. We put in our E naught. And again, this is the Nernst equation, the simplified form of the Nernst equation, because we're doing it at the room temperature. So we don't have to, put in extra work. And then that's that constant divided by 2. Everybody understands why that 2's there? Comes from here. Okay. All right, and that's the log of the species that would matter in this reaction quotient, right? So we look at the water one. This is a pure liquid. H2O is pure liquid, right? So that's unity 1. We don't have to do anything with it. H2 is a pure gas. H2 is our gas right here. That's 1 bar, isn't it? And then we have OH minus here. So our reactants are the only ones that matter because the water is unity, right? So we have the pressure over H2 times the concentration over OH minus to the 2nd power because this is a 2 in front of the OH minus, right? Everybody good so far? It's divided by 1 because that's unity, right? Okay, we plug in all our values. Luckily, the pressure of H2 is also 1, so that makes life easier. That's the concentration of the OH minus right there. How do we get the concentration of the OH minus, by the way? We have pH, don't we? So we do POH. 14 minus 10 is 4. 10 to negative 4, right? Okay. To the 2nd power. We solve, and we get this for our voltage. Okay. Notice this value will be less than 1. This will make it a negative. And so we should expect something less negative for our voltage, right? It's one of the ways you can make sure you don't screw up the calculations, because these things get a little bit lengthy to put in calculators, right? Okay. Next we do the anode. Again, we have our E naught, Nernst equation. This is 2 again because we had to match those electrons. Log of the I minus versus the I3 minus, right? Remember, the I minus had power of 3 because that's coefficient 3. These are both concentrations. They don't go to unity. They're not pure solid or liquid, right? They're in solution. So we plug these values in. The I minus is the Ki concentration, formal concentration. The I3 minus is actually given to us, isn't it? Remember that? It was 10 to the 5th up here. Right there. We plug them in, we do our math, and we get 0.49. Well, then we just do it like every other system, right? Every other cell. So we take the cathode minus the anode. So cathode right there minus the anode, that's going to give us negative 1.081. By the way, this is why your book typically does not change the signs here, if you're ever curious. It's because you'll have to do work here where you don't want to flip the sign. Okay? Flipping the sign at the end is the best way to do it. All right. So, what does that mean? Well, we're going to have to apply at least negative 1.081 voltage to force the reaction to occur. However, keep in mind that if you did apply this negative 1.081 voltage, would the reaction necessarily occur? Let me put it a different way. Does your gasoline burn right now while it's in the car with nothing to get it started? No. Why is that? Activation energy, right? Yeah. So this might not actually overcome activation energy. So this may not actually cause the reaction to occur. Yeah, this would be under ideal conditions, no resistance, no polarization. The activation energy is just enough for the tail ends of this energy. Remember, every time we talk about energy, it has tail ends. There's high and low, right? We're talking about averages. So it's possible that if you have all these other factors low enough, you could get the reaction going very slowly. And this would be the amount of energy that you would need to drive the reaction forward without any other concerns like, resistance. But in reality, if you were to apply one of these voltages we've done, almost none of these cells would actually run. They would not work, okay? Because you have resistance in the real world, right? By the way, if you ever get a system for like a solar system that handles charging batteries, it will actually have settings in it for these terms. They call them slightly different things, but like the overpotential and the ohmic potential, they have terms in there that you put like the resistance of your battery. Because it needs to use that to charge the battery, right? If it were to just sit there and apply the voltage you would predict for that battery, it would never actually charge. Or you get very, very slow charging, okay? So what you would do in an experimental situation, if you predicted this, you would actually slowly ramp up your voltage until it starts going, okay? But just a little. You don't want to just go, 3 times. Because then you can get other reactions, right? Okay. And that's why you have a professor, by the way. I don't think your book makes that very clear, does it? That this is actually more like a minimal voltage you would need. Now, to be honest, this isn't necessarily minimum voltage. The reason I say it's kind of like and not it is a minimum voltage is because, remember, energies always have a bell curve. There's always a tail end on the high end. And so it depends on, how far that tail end goes out, okay? You could get a reaction with even a slightly lower voltage. It'd just be slow. And it depend on the cell. Now E cathode is unchanged, but E anode changes because the I3 minus is different from the I3 minus in bulk solution. So you notice B had a different concentration, didn't it? See that? That's 10 times the amount. So we have 10 times more I3 minus. That means the voltage on the anode side is going to be different. So again, we reset up our Nernst equation, but the I3 minus term on the bottom here is 10 to the negative 4, right? So we do our math again, and we get 0.520. I mean, not a huge difference, but it's a noticeable difference, isn't it? All right, so the next part is we now need to use the E cathode minus E anode minus IR minus over potentials, right? Because we're now trying to figure out exactly what we would need to get this going, okay? And we now have all these other terms. That's what all this stuff was, by the way. See the ohms right here, there's cell resistance. Well, that's the resistance of our cell, right? that. That's the IR. Okay. So we plug in our numbers. Negative 591 volts comes from the previous problem right here, because that didn't change. This one changed, so it's that one right there, because our I3 minus changed. Did I lose you?
Oh,
yeah. Because yep, you got it. Because remember, our I3 minus got 10 times the concentration. So that's going to change that voltage. That's a concentration cell, by the way. That's what that. Okay. This right here, what we have as resistance, but resistance scales on amps, right? That would give us voltage. So we need to take our resistance and multiply it by our voltage. Please note that you will almost never be given the right damn units for this, okay? Because just electricity work in general, people are very, very conscious of keeping a ones place here or only a single decimal place. And so you always see like milliamps. So you have to convert that to amps almost every fucking time. And you may end up with like milliamps or mega ohms or milliohms, one of the two. And then you have to do that as well. But so ohms times amps, that gives you a voltage, right? Remember, you always need to be in a voltage because you're working in voltages, right? Okay. Be careful about that. It really is something that will get you, okay? Then we look over here. We have our overpotentials. Those were listed right here. See that? Okay. So those were our overpotentials. They get subtracted off, just like the formula says, minus overpotentials, right? It doesn't matter whether they're the cathode or anode, okay? Because they're overpotentials. The amount of extra energy you have to pump in that to overcome those cathode and anode, okay? The excavation energy you pump in at each side of the reaction. Okay, so we go ahead and add all that up. They're all negative terms. So, I mean, you can just directly add them, I guess. And we get negative 1.644 volts. Notice how different that is. Was that more than you thought it might be? See how different that is? It's like more than 50% difference. So what did we just learn? If we apply negative 1.081 volts, that's probably not going to do it, right? In fact, we needed to apply negative 1.644 volts to drive this reaction. Okay? Much closer to the ballpark, yeah. This would be pretty accurate, probably. These look like they'd probably be experimental values anyways, right here. So those are probably pretty good numbers. Yeah. You know, any experiment, if it's an experimental number, they should be very close. Give or take some change due to the fact that maybe your materials have changed or conditions have changed slightly. You know, you're never actually 25 degrees. You're always like 24, 26, right? Yeah. Yeah. So that's life. That's real life, right? They'll always be in the ballpark. Everything's an approximation. By the way, though, they have gotten actual solving of some of these systems now. Typically, it takes a quantum computer to take all the variables in, and it can get very expensive to do, but they're getting pretty close to quantum computers. And there's pseudo-quantum computers now, which is pretty crazy. But yeah, they finally solved the energy for like 3 different molecules now. They're the simplest ones, though. Hydrogen, H2, and helium. I think they're working on the next one up, but I haven't seen anything from it. Maybe I just missed it. So controlled potential electrolysis is conducted in a 3-electrode cell. The potential of the working electrode is going to be measured with respect to a reference electrode to which negligible current flows. The current flows between the working and auxiliary electrodes. So this is what that looks like. This is a 3 electrode cell right here. Okay? And so what do we see here? Well, we see our working electrode. We then have a reference electrode. That's our reference. And that's our potentiometer. That's going to tell us, the difference in potentials between them, right? So then we have a working measurement, okay? So this will allow us to measure. This is our measuring stick. This part is actually going to do the work, okay? And notice this is a potentiostat. That's something you can dial up the voltage on, okay? By the way, be careful about using potentiostats whenever you get to doing them. You really have to pay attention to what range they operate under. Because, you can actually put more amperage across something and it'll just heat up. But if you put more voltage across something that can handle, electrons will start jumping circuits and fry stuff, okay? So you really have to be careful about that. Which is funny because it's the exact reverse of a human. A human, we can have huge voltage differences across our body, but even 40 milliamps will kill us if it goes through the heart. So we can take barely any amperage, but we can take huge voltages, right? Like 10,000 volt stun taser, right? But if a computer takes a taser, it's done. Goodbye. Yeah. In fact, actually, people use that to clear computer systems and microwaves. Yeah. So an electrogravimetric analysis, analyte is going to be deposited on an electrode whose increase in mass is then measured. So you'd measure the electrode, you'd do a redox reaction where it plates out on the electrode, and then you measure the electrode again. That difference in weight would then be the amount plated on, right? So this test for completion of the deposition, the disappearance of color and no deposition on a freshly exposed electrode is how you would test for whether this is done or not. Because you can't just go, oh, it's 10 minutes, now you're done, right? Because your reaction conditions will change things like that. That's that rate of reaction. It depends on all sorts of things like this temperature of the room, right? How well it's being mixed. Depends on things you don't have good control over. So what you do, many of these ions that are in solution will be colorful, right? Like copper. You guys remember copper, right? No? You remember your iron ones you've seen now, right? Yeah. So you can have a colorful solution. When the color disappears, what does that indicate? You've used up your metal, right? Like if you have a copper solution, it was blue. Now it doesn't have any blue left. You've used up all your copper, right? Okay. The other way you can do this, and this is a more accurate measurement, is you can do it kind of like how you do the burning the crucibles. So you run the reaction and see if there's any extra mass that got added. Okay? And typically what you do is these electrodes are pretty easy for most systems to replace. They're just copper, right? So you would take one out, get it ready to measure after you've done the gravimetric, you've plated out the metal, and then you just measure a new one and attach it and put it in. Okay? And these copper electrodes can be very standardized and actually cast out of the same metal, so you can get a whole series of these very easily that are extremely standard. There's no difference between them except for slight mass differences, which is quite nice. You can measure the mass differences, so no biggie. This is a surface or qualitative test for analyte in solution. This right here is an example of this. of one of these cells. Okay. So with a constant voltage in a 2-electrode cell, electrolysis is not very selective because the working electrode potential changes as the reaction proceeds. So to prevent the cathode potential from becoming so negative that unintended ions are reduced, a cathodic depolarizer, such as something like NO3-, can be added to the solution. The cathodic depolarizer is more easily reduced than H3O+. So essentially, this keeps you from doing other reactions there that you don't want to do. Okay? Alternatively, we can use a 3-electrode cell with a potentiostat to control the cathode potential and prevent unwanted side reactions, which is the one I showed you before, right here. And that's why most of these systems are set up like that. Okay? This allows you to control that and change over time. Okay? Remember, you're going to be changing concentrations, right? And so your voltage you need changes as you do this. It also changes because of polarization at the cathode. Okay? Okay, so when cathode potential is required to reduce 99.99% of 0.1 molarity copper 2+ to copper solid, is it possible to remove this copper 2+ without reducing 0.1 molarity SN10 2+ in the same solution? So we have two stages to this problem, right? What's the cathode potential for the copper? And then how does that compare to the potential of the tin? So we need to go ahead and get the redox reactions for both of these. We have the copper here, we have the tin here. There we go. And we have the E0s for these. Notice they're not too similar, but they're not that far apart, right? So if 99.99% of the copper 2+ was reduced, your concentration of remaining copper 2+ is going to be 1 out of 10 to the negative 5, right? So it'd be 1 over 10 to the negative 5 for your Q, your reaction quotient, in your Nernst equation. So we set up an E cathode equals E0 minus, we do the 25-degree version because that'll work fine. We'll have less terms we have to put in. Temperature doesn't change, right? So it doesn't really matter what temperature we do it at. And the N is 2 because 2 times E. So what does that say to us? Well, that says under these conditions, our Nernst equation says that we're going to get a 0.19 volts for the E cathode. Okay. So let's look at the cathode potential that would be required to reduce SN2+. So again, we just set up another Nernst equation, right? E cathode. It's going to be the E0 here, minus, again, blah, blah, blah. The only difference is the concentration, right? So the log of 1 over the concentration of the SN2+, which was given to us right here, 0.1, right? And what do we find out? Well, we would get a negative 0.17 volts. So in this case, we would not expect the reduction of SN2+ at a cathode potential more positive than negative 0.17 volts. The reduction for the copper is more positive than that, right? And so we would not expect the 10 to reduce until well after we've reduced 99.99% of the copper, okay? I.e., yes, we can do this. We can plate out the copper without getting the tin, right? Okay. Note, this will not always be a yes, okay? These were, luckily, one was negative, one was positive. and so that wasn't as much of an issue. But if this had even been, you know, a positive value, anywhere close to 0.19, then that would have been a real question, right? Coulombetry. Coulombetry is the number of moles of electrons that participate in a chemical reaction are measured. Notice the coulometry, literally coulombs, which is a count of the number of electrons, right? Okay. So literally metry, measuring, coulombs, counting electrons. For example, the cyclohexene can be titrated with Br2, which is generated by electrolytic oxidation of Br minus. So this would then give us an endpoint, which is the endpoint will be indicated when excess Br2 forms, which would then react with the cyclohexene. The generated Br2 will react to cyclohexene, and we can measure the amount of cyclohexene. Thus, it will react with cyclohexene until the cyclohexene is consumed. So the total electrons produced to reach the endpoint are then going to be related by stoichiometry to the amount of cyclohexene in the solution. In this case, you would need 2 electrons for every Br2, which is 1 Br2 is 1 cyclohexene, right? So it would be 2 electrons for each of the cyclohexenes that are reacted. So that gives you a nice stoichiometry. Very good. If you're wondering about the cyclohexene, notice that that is nonpolar. It's very easy to measure the weight out for that. We can use the weight and the formula weight to determine the moles of cyclohexene we measured out for it. So that's actually a very nice standard to use. And this is actually a very quick reaction. You guys have actually done this reaction a few times. Do you guys remember that in organic? You've done a very similar reaction. This is like a reddish liquid that you then put in and it goes clear. Maybe not. Good. Yeah, it's a very distinct, nice reaction, right? It goes very fast, and it goes very well to completion. Great reaction to use, actually. Works nice. So the reaction is going to be carried out at a constant current with the apparatus in 17.9. You may have to flip back for that apparatus. We mentioned it quite a few times. Hopefully you got a general idea, okay? The Br2 generated at the platinum anode at the left will react with the cyclohexene. When the cyclohexene is consumed, the concentration of the Br2 suddenly rises, signaling the end of the reaction. This would do several things. There's several ways of actually detecting this concentration of Br2 rising. It would most easily and quickly be detected by measuring the current between the 2 detector electrodes on the right of figure 17.9. If you get a rapid rise in that current, you know your reaction's over. Okay? The other way you'd probably notice is it'll start turning red. It'll start turning wine red. But by the time you notice that, you've overshot considerably. Okay? So if you do see it start turning red, you screwed up. All right? That's how you know you messed up. All right, so this is the detector anode right here. This is the detector cathode right there. Notice they're opposites. Okay. So this would be a sample current polarography. So what you see here is the potential versus time. This is a very common looking diagram. And see how it forms steps? So this is the drop time here, it's 1 second. Sampling takes time as well. In this case, our sampling takes 17 milliseconds, which when you're talking about 1 second steps is actually significant, right? So keep that in mind. Sampling always takes time, right? It's not instant. Okay, in this case, we see the step height is 4 millivolts. What you're looking at here is these currents right here. So you have the Faraday current and the charging current right here, and they're slightly different. Okay, let's do a colorimetric titration real quick. So 2 milliliters of volume containing 0.6113 milligrams of cyclohexene per milliliter is to be titrated in our figure, which is at 17.9 again. How much time is required for the titration at a constant current of 4.8245 milliamps? So this is literally just a normal titration stoichiometry, right? So we have 2 milliliters, and this right here is a concentration, isn't it? So weight versus molarity. And so we multiply those together, canceling the milliliters. The next thing we have to do is we have to figure out how many millimoles there would be for cyclohexene in that many milligrams, right? How would we get that? This number here, where do you think that comes from? The milligrams per millimole. What if you cancel the milli? We have milli on top, milli on bottom. Those will cancel, wouldn't they? So we have grams per mole. What do we call that? It's a molar mass, right? It's just a periodic table molar mass, isn't it? We can take milli on both sides, so then we can use it with the rest of these numbers. Okay, so then we solve for the millimoles here, right? We have the reactions. They were on the 1710, 1711 that we just talked about. It was that 2 for 1. So 1 molecule of cyclohexene would require 1 molecule of the Br2. To generate the Br2 requires 2 electrons, right? So the next thing we're going to want is equation 17.3. This relates the reaction time to the moles of the reaction. So remember that one that I said that just use this equation, it'll make your life easier? Okay. It was last lecture. It was at the very beginning of this material. Okay. So it's the moles of cyclohexene equals the current times the time over N, which is the number of electrons, times Faraday's constant, right? This is a constant. This is what we're looking for, time. This is that current that it tells us right here, which is in milliamps right there. And N is, well, 2, right? 2 electrons. We plug these in. So we get time on one side. We get the other terms on the other side. Remember, Faraday's constant is a, well, constant. We plug each of these numbers in. We just got our moles right here. Notice this is in millimoles, so the number here is 10 to the negative 3 moles. See that? Number of electrons, Faraday's constant, and this one right here is that wonderful current right there. Notice again, this is a milli, so it's that number times 10 to the negative 3, right? An interesting side note, these actually cancel. The 10 to the negative 3s on the top and bottom cancel, right? And that oftentimes happens. So if you write these out, you can just cancel this with this. By the way, the coulomb per second, that's just amps, right? we've just rewritten amps, coulombs per second, so that our units would cancel and give us the right unit, which is seconds. Anybody have any questions? Yeah, practice. So, you can turn that into minutes if you want. Divide by 60 seconds per minute, and we get like 10 minutes, right? All right, so what are some of the advantages of coulometry? It's precise, it has high precision, it has high sensitivity, the generation of unstable reagents in situ. The Latin in situ, by the way, means in place, which you guys are biochemistry, so I'm sure that you know that. The reagent is used right where it is generated. Everybody understands why that's a big advantage, right? Yeah. You don't lose reagent to oxygen in the atmosphere that way, right? You don't lose it because it was sitting on a shelf somewhere. You don't lose it because of 100 different reasons, right? So it allows you to generate it in place, do the reaction right there. Okay? We actually did that quite a bit in situ generation of a reagent, quite a bit in organic chemistry, didn't we? We just didn't use electrodes to do it. We used a unstable reactant that would react under those conditions, right? And give us that reagent. So types of coulometry. In a coulometric constant current titration, the time needed for complete reaction measures the number of electrons consumed. And that's the one that we've actually talked about so far. That's the one we just looked at, is a constant current one. Okay? Controlled potential coulometry is more selective than the constant current coulometry, but slower. So remember, when you're doing these, you're going to decrease their concentration, right? What does that do to your cell? It would drive up the energy needed, wouldn't it? Remember, the reaction won't go as fast, right? So what does that mean? Well, in a constant current one, you're providing that same amount of energy, even though you need less electrons over there to actually do the reaction, because you have less molecules to take the electrons on, right? Okay. But in a controlled potential coulometry, you're going to take more time to do it, because it's going to take longer because you're not providing as much energy to do it, right? But it's going to be more selective, because instead of providing extra electrons, you're providing the amount of electrons you need, right? That making more sense? I know it's an abstraction, but I think it's a helpful abstraction. So electrons consumed in the reaction are going to be measured by integrating the current versus time curve. So amperometry. I always have trouble saying this. Amperometry. There we go. In amperometry, current at the working electrode is going to be proportional to the analyte concentration. So the Clark electrode is going to measure dissolved O2 by amperometry. This is a famous example of amperometry, okay? Is the Clark electrode. Probably the more famous one nowadays would be the glucose biosensor. This generates peroxide by enzymatic oxidation of glucose. And the peroxide is then measured by amperometric oxidation at an electrode. Okay? Okay, let me just finish this and we'll go. A mediator is going to be employed to rapidly shuttle electrons between the electrode and the analyte. Okay? Anyways, that's it. I'll see you guys Wednesday, I guess. And you have a great day. Thank you for letting me know.